Okay, so let's go back to the slide after these different examples and the definition, the general definition of a path of on a cycle. So a path, P sub n, is a graph in which we have n vertices and we have edges that connect the first vertex to the second to the third, and so on. Okay, and then it contains n vertices, n plus 1 vertices, n edges, and all the vertices are of degree 2 except the ones that are at the beginning and at the end, which are of degree exactly 1. Okay, so this is another situation in which we can know the different numbers of the graph. The number of edges is n, the number of vertices is n plus 1, and the degrees are either 2 or 1, okay, depending on whether they are terminal, they are at the end, or they are in the middle of the path. Okay, in the case of the cycle, then we have n vertices in which the edges connect the vertex to the very next vertex and to the previous vertex, taking into account that the next vertex to the last one is the first and the previous vertex to the first is the last. Okay, so they form a cycle. The number of vertices is of course n, the number of edges is also n, and the degree in this case is 2 for all the vertices because each vertex is connected to the next and to the previous one. Okay, so again we can know all the numbers of the relevant properties of the graph just from the definition. Okay, so if we know that we are dealing with C10, for instance, we know the degrees, we know the number of edges, we know the number of vertices, and so on. Okay, and the final type of graphs that we are going to study is what we call hypercube graphs. We call these graphs hypercubes because they are the generalization of the connection of the different vertices of cubes in different dimensions. Okay, so we can have the usual cube in dimension 3, and if we take the vertices of the cube and the way these vertices are connected, we form a graph. Okay, in this case we have let me draw it. We have something like this, right? We have these vertices on the front face of the cube, these vertices on the bottom face of the cube, and they are connected like this, right? So this is what we call the graph for dimension 3, the cubic graph Q3. Okay, but we can generalize this to other dimensions. How to do this? Well, here we have a definition, a recursive definition that can seem a bit complicated, but you will see that it's very easy. The idea is that we start with Q0. Q0 only has one vertex. Okay, this is Q0. To form the next cubic graph or hypercubic graph, what we do is we make two copies of Q0 of the previous hypercubic graph, and we join the vertex that are the same in both graphs with an edge. Okay, so here we have made a copy of Q1, two copies of Q0, and we have joined the two vertices in order to form Q1. Now to form Q2, I make two copies of Q1, and I join the vertices which are the same in both graphs. Okay, so this one with this one with this one, and we take Q2, which of course is a square. Okay, that is the idea that we have of a cube in dimension 2. Okay, if now I make two copies of the square and connect the corresponding vertices, that is exactly the way in which I draw the cubic graph of dimension 3 before. Okay, we get the connections of the different vertices of a cube in dimension 3. If I do the same with dimension 4, what I'm not going to do, you can do it on your own if you want to, but here we have an example of two cubes connected in a way that we form the Q4 hypercube graph. This is also what usually is called the tesseract. Okay, maybe you know that name. It's a name that appears in, for instance, some popular movies that you may have seen. Okay, so this is what we call the four-dimensional cube, the hypercube, or the tesseract. And then if we connect two, we make two copies of Q4, and we connect the corresponding vertices, we obtain Q5, and so on. Okay, so this is also an interesting family of graphs, because they are examples of some of the properties that we have been studying in some cases, and they appear also in connection to some other methods and properties. Okay, so they are interesting and important for us in different ways. And as a final exercise, in addition to finding out the number of vertices and the number of edges and the degrees in the case of the tournaments, in the case of complete bipartite graphs, I want you to try and answer two questions. First, what are the numbers, the relevant numbers in this case, in the hypercube graphs? What are, if I give you Qn, what is the number of vertices? What is the number of edges? And what are the degrees of those cubes? Okay, of the graph Qn. But also I want you to answer another question. Is the cubic graph, the hypercubic graph, bipartite? And if it is bipartite, in which cases? Okay, so please try to solve those exercises on your own. First, find the number of edges, the number of vertices, the degrees of both the tournaments of a given number of vertices and of the Qn graphs, and then answer, if I give you Qn, depending on n, when is it bipartite and when it is not bipartite. Okay, I will upload a different video with the answer to these questions. Thank you very much.